Welcome back to another lesson on limits. In this lesson, we're going to delve a little bit deeper in finding limits from graphs. And you learned in the last lesson the definition of a limit, and you did look at limits on graphs in the last lesson, so we're going to take it the next step with one-sided limits. What is a one-sided limit? Well, a one-sided limit is the y value, or the height that a function approaches as you approach a given x value. Well, that's still all the same as from the last lesson, but this time we're going to approach either from the left side or the right side. So instead of saying just in general coming in from both sides, I'm just going to say what happens if I come in from the left side or what happens if I come in from the right side individually. And if that sounds confusing, it'll make more sense once we look at an example. So let's take a look at example number 1. I want to find the limit of f as x approaches 3 from either side. So I'm focusing in here on my x value of 3, but I'm only going to take it one side at a time. And we can see that this is going to be relatively important because I don't actually have the same value. I've got a jump discontinuity here. I've got two different values going on depending on which side I'm coming from. So it says the limit of f as x approaches 3 from the left side is -1. So how do we see that on the graph? Well, coming from the left side, here I'm to the left of the 3, and I'm coming in this direction along my x-axis, getting closer and closer to 3. So if I follow it along the function then, from the left side, I see that the y value that I get closer and closer and closer to from the left side is -1. And I'm going to write that using my limit notation as the limit of f as x approaches 3 from the left side is going to be an exponent of a negative. So it's just kind of strange notation in terms of it's hanging out here all by itself, but it's 3 to the power of negative. Says I'm approaching from the left side. This is an exponent negative. From the left side is equal to -1. There's my y value. And then if I take another look and I want to know, okay, coming in from the right side, coming in from the other direction towards 3, if I trace in along my function, the y value that I get closer and closer and closer to from the right side, coming in from the right side, is now going to be a y value of 2. So the limit of f as x approaches 3 from the right side is 2. And I'm going to write this limit of f as x approaches 3 from the right, an exponent of plus. I can't write this as small as I'd like to, but an exponent of plus, and that's now going to be equal to the y value of 2. And if we wanted to ask, okay, well, if I have two different values, the two sides are different from the left, from the right. One I get -1, the other one I get 2. What's the general limit as f as x approaches 3? So what's the limit of f as x approaches 3 from both sides? Well, in this case, because the numbers are different, the general limit does not exist. We don't find the average. We don't choose the one where it just happens to be defined at 2 instead of open circle at -1. No, it just does not exist. If we've got two different values from either side, the general limit does not exist. All right, let's take a look at a few more examples. Example number 2. I'm looking at letter A, which says the limit of f as x approaches -2 from the left side. So I find on my graph here's -2, and thinking from the left side, coming from the left, tracing along my function from the left, I get to a y value of 1. So the limit of f as x approaches -2 from the left is -1. Going to take a look now at the limit of f as x approaches -2 from the right. Remember, this plus means from the right side. Now coming in from the right side, I'm going to trace along my function from the right side, and I get closer and closer to the y value of -2. It's kind of hard to read the scale, but hopefully you can count along your axis. Y value of -2, which tells me that the general limit as x approaches -2, these two numbers are different. I've got a jump discontinuity, is going to do not exist. And DNE is just a abbreviation for does not exist. I realized I wrote a -1 here. This should be +1. This is actually a positive value 1. Sorry about that. Okay, another example, the limit of f as x approaches 1. So this doesn't have a plus or minus, meaning we need to approach from both sides. So from the left side, as I'm approaching 1, here's my 1 here. I'm going to trace along my function, get closer and closer and closer to y value of 1. So that's fine. That's from the left side. From the right side, trace along my function, get closer and closer and closer. That means I'm getting close again to 1. That means the general limit does exist and is equal to 1. Doesn't matter that there's a hole here, doesn't matter that there's this dot down here. I'm not interested in where the function actually exists at that point. I'm interested in what the limit is as I come from both sides. The limit, letter E, of f as x approaches 0, again from both sides. Well, my function here, this would be x at 0, is defined here, continuous here. So this is just the same case as what we did yesterday in terms of from the left side goes to -2, from the right side goes to -2. It's just going to equal -2. Limit as x approaches 3 from the left side. So I'm going 1, 2, that's going to be here. This is x approaches 3. Again, coming in my function from the left side of 3, coming up towards the right, but from the left side, hits a y value of 5. Then it asks me, what's the limit of f as x approaches -1? -1 would be right here. Again, function is continuous. No holes, no asymptotes right here. So this is just going to be, again, from both sides, I end up at -3. F of 1 is saying, where is my function defined at the x value of 1? This is a different question than what's the limit of f as x approaches 1. This is just what is f of 1. So here is x value of 1. And if I look for where my function is defined, there's a hole right here where the limit was, but there's a dot down below. This is the actual value that I'm interested in for where's my function defined. So f of 1 is equal to -2. Now the fact that this f of 1 is a different value than the limit tells you there's a discontinuity here, but it doesn't stop there from being a general limit or stop the function from being defined at that point. And f of -2, well, I'm looking at -2, I've got a dot up here and an open circle down here, so I'm going to gravitate towards there's the dot, and that's going to give me a y value of 1. All right, so hopefully that's kind of becoming clear. We'll get more practice at this as we go along. Example number 3, sketch a graph of the function g that satisfies all of the following conditions. So things get a little trickier here when you have to make the graph that matches these conditions, but we'll take them one at a time and then we'll just double check to make sure that we got them all. So condition A, g of 3 equals -1. So really all this is saying is that I have the point on my graph of x value of 3, y value of -1. So that's easy. I just find x value of 3, y value of -1. I'm going to put a point here. My graph needs to go through that point. At some point, somehow, going to get there. Letter B, g of x equals 4 when x approaches 3. So I've got limit of g of x as x approaches 3 equals 4, meaning I'm going to get closer and closer and closer to an x value or y value of 4 when I'm taking the limit as I get to 3. So it looks like my function is not going to be defined at 3, 4, but my limit is going to approach this open circle. Now I don't know if it approaches from below, if it approaches from above, if it approaches straight over, if it leaves going up, leaves going down. I don't know that yet. So I might just put these little lines here to say I need to connect this up somehow, but I'm not sure exactly how it's going to connect up, and I might need to change them later on. So this is when it's always a good idea to use your pencil so that if these lines end up being in the wrong direction, that I can change them later. But for now, I'm just going to put them there as placeholders to remind me that I need to connect up to here and not to this point down here. Then letter C says the limit of g as x approaches -2 from the right side is 1. So I'm getting closer and closer as x approaches -2 from the right side, being a y value of 1. So again, I'm going to put an open circle here. I can always fill it in later if it turns out that my function is defined here, or it might not matter whether my function is defined here, as long as the limit as x approaches -2 from the right side, so I'm going to connect up from that side, is equal to 1. And again, I don't know where it's coming out, if it's coming out up, down, weird ways on the other side. I just know that I'm approaching it from the right side. I might not even connect it on the other side. So for now, I'm not even going to put any lines over here, just in case. Okay, letter D, G is increasing on the interval from -2 to 3. So between the interval of -2 to 3, G is going to be increasing, going up. So that's where I get to connect up these two lines and say, okay, I'm going to be increasing until I get to 3. All right? So increasing from -2 to 3. So it could be doing anything in between, but now we know that it's increasing. And you can kind of decide what shape. You could have actually done a straight line there. It's up to you, just as long as it's increasing. And then my last condition, the limit of g of x as x approaches -2 from the left side, so now we're thinking about what happens as we come in towards this x value from the left side, has to be greater than the limit of g of x as x approaches -2 from the right side. So in other words, we don't really know what's happening over here. We just know that it ends up being somewhere greater means greater, y value means higher. So you can decide where along here you want to put it, but we can't put it down here below. It needs to be above my y value from the right side. So I might just put it here at 3. And I know this is the limit as x approaches to -2 from the left side. And again, because this is our last condition, we don't have a clue what's going on this side. Could be constant, could come up, could come down, who knows. Doesn't really matter. But just as long as my limit as x approaches -2 from the left side is greater than from the right side. That's my last condition. So I could fill in either of these circles or leave them both open because they don't actually tell me here if my function is defined in one of these places, or I could just leave it as a hole in both places. And on this side, I'm just going to continue this on however I feel like till it goes off the graph. Okay, let's double check all our conditions and make sure that we actually did do what we're supposed to do. So g of 3 equals -1. So if I go to 3, I'm actually defined at -1. Check, got that one. The limit of g of x as x approaches 3 is 4. So as I take the limit as I approach 3, I actually get to the y value of 4 from both directions. So check, yep, we got that figured out. The limit of g of x as x approaches -2 from the right side is 1. So coming from the right side is 1. Yep, check, got that. G is increasing on -2 to 3, -2 to 3, increasing all the way. Yep, got that, check. And the limit of g of x as x approaches -2 from the left side of -2 from the left side, take your left hand and go towards the left, towards the right, is greater than the limit as we approach from the right side. Check, got that too. So always a good idea to double check that you've met all the conditions, and this graph could end up looking in several different ways as long as we meet those conditions. So your graph may not look exactly like what you might see in the answer key, but as long as you've met the conditions, you are good to go. All right, and now it's your turn to practice with the practice questions. Limits from the left, limits from the right. You got this. Good luck.